Hi, and welcome back. So let's continue on this third part, solving this example 2.24, which is about a simple two-axis planar robot. So on the part one, we have just drawn this illustration of this robot and also assigned the axis needed on DH representation, and assigning this axis we have turned these joints into frames. So we assign Z axis and X axis into the joints, and this way we turn it into frames. And this is very important because if we have these frames, we are able to put this configuration into a reference system so we can track the motion of the robot and also program this robot. So for example, let's say we want that this robot, it needs to perform some certain task, and on the real world we use measurements to to program the robot. So let's say, for example, right here on the in the factor, we we can attach it a tool for grab some object, and this object, it has some certain distance of this tool, so we need to program the distance of the end effector of the hand of the robot of this tool to the object. So we need the information of the lengths of the links. We need information of the angle that the links need to rotate to be able to not only grab the object but place this object into another place. And this is why we need to assign this axis and turn these joints into reference frames. And after assign this axis, which is a requirement of DH representation, the next step of this type of solution technique. So DH is a technique that we use to represent robots, and its advantage is that we can represent any number, any type of robot with any number of joints and links. So the next step of this technique is to follow a procedure, which is a sequence of 4 motions, and this is generical. So it's a general procedure. So we always have these 4 motions. So after we do these 4 motions on the system, we accomplish the task. We accomplish our transformation from one local reference frame to the next one. So for example, right here is the end effector, is the hand of the robot, and we can write a transformation right here, which is a transformation of the H frame in relation to the frame 1. So this frame we are assigning as frame 1, and notice that this frame is a reference to this frame. So right here from the hand, from the end effector to 1, we are doing a transformation, and now this frame it turns into a reference to this frame. So we can do a transformation of the frame 1 in relation to the frame 0. So after assign this axis and turn these joints into reference frames, we apply these 4 motions, which is a sequence, and we need to follow the sequence. We cannot apply, for example, the second motion as the first one. We need to follow this sequence. This is very important. And after this, um, after that, we have accomplished our goal, which is transform from one local reference frame to the next one. And actually, we stop right here, and I find a way to stop this using duct tape. But also, I wanted to correct me something. And this is, it won't disqualify what I have already explained right here to you. It's only that theta 1 and theta 2, as they are unknown, because they are the angles of the revolute joints. Actually, we don't know its angles. So this is our variables. And what we know is alpha, which is 0, and also D, which is also 0. From here, from this sequence, we know that alpha and D, they are 0. And let me again grab this characteristical matrix, which is the solution for a transformation from one local reference frame to the next one. So with this matrix that we have calculated in previous lessons, we are transforming from one local reference frame to the next one. So if you remember, this matrix is the product of the transformations. So with these 4 motions, which is traduced into transformations, so each of these motions on the sequence of these 4 motions, each of these, they are representing a transformation, either rotation or translation. It can be a rotation or it can be a translation. And again, in a sequence, so a sequence is composed of a rotation, so this is the first motion, a translation as the second motion, again followed by a translation as our third motion, and the fourth and last motion, again a rotation. So this sequence of these motions they are transduced into transformations, and with these transformations we write this total transformation matrix, which is also our kinematic equation. So the transformation equation right here also, it will be our forward kinematic equation. Or also our total transformation equation. Okay, and after write this total transformation equation or our forward kinematic equation, we write this equation with these matrices and multiplying these matrices. So also you can notice that when we do a motion, after we do another motion, and this is on this operation is analog to a multiplication. So we are doing four motions, and this is analog to these four transformations, which is analog to these matrices, and a sequence a sequence of motions is analog to the operation of multiplication. And after this operation, we obtain this matrix, which is a characteristical matrix of a transformation. So this transformation um, is the result of a transformation. So we apply this matrix if you wanted to transform from one local reference frame to the next one. So right here we got t and index n plus 1. So that means that if we start from a local reference frame that we are assigning as 0, so 0 plus 1 is theta 1, and from now that we are on theta 1, so if we got one more joint, so this is turned into theta 2, so this is for any number of transformations. So this is not for links or joints, this is for number of transformations. So it's not for link and also not for joint. This is for the number of transformations. And we got another notation, which is A, which is also, it means a transformation. So A n plus 1, it means the number of transformations that we are doing in a system with certain robot with any number of links and joints. So again, this is the advantage of using DH, because we can represent any type of robot arm, for example, with any number of joints and links. So, okay. Okay, right here. On the last video, I said that for this solution of this first transformation, A1, is also solves for the second transformation, A2. But actually we can do for each of these data, sorry, I keep right here, data 1 and data 2. So let me copy this again. First for data 1. So right here, we'll just use C1, S1. Let's already substitute what we can substitute right here. We know that alpha is 0, so let's substitute for all alpha, alpha 0, and D also is 0. So solving for the first data 1, and also facing this as a generic solution that can solve for any value of data. So cosine of 0 is equal 1. Okay, and sine of 0 is equal 0. So cosine of 0 is equal 1. So right here is 1. And sine of 0 is equal 0. Right here, cosine of 0 is equal 0. Right here, again, cosine of 0 is equal 0. And cosine of 0 is equal 1. And D is also 0. And this is the matrix for the first transformation, which is the transformation of the frame 1 in relation to the frame 0. A generic solution for any value of data 1. Okay, and for the transformation of the frame H in relation to the frame 1, which is the transformation H2. So again, the values, they are the same. We just need to change right here the index. Now let's change for 2 because it's for data 2. And this is why I said that this solution also solve for data 2. So is a generic solution to solve for any value of data 2. So C1, 2, S2. Right here we don't have data, it's just C and S. Let me correct right here. One. Okay, and now we are ready to solve this using the octave. Okay, and we have just done the same right here. Okay, now open up your octave and first, yeah, we can clean the octave's memory. So type clear all and CLC to clean the command window. Now type pkg load to load the package, and the package is the symbolic. So type pkg load symbolic, enter, and type sims. Now C1, C2, A1, A2. We also need S, so S1 and S2 also. And press enter. Okay, now let's work on the matrices. So A1, I have already prepared these matrices right here. Don't forget to add the sign on the sign. So let's copy first A1 and paste. Okay. Now the second matrix. Okay, and now let's just multiply these matrices. A1, so type A1 times A2. Okay, and let me just take a print screen and compare with the result of the book. And it's all correct. And let me separate this by columns. So this is one column, this is another column, right here a third column, and all this is the fourth column. So let's write the solution. So the total transformation, which is the transformation that is transduced on the whole motion of the robot, that this robot does to accomplish certain task, is given by the transformation in relation to the end frame to the frame 0, which is the frame that we are, is the last joint, is the frame that we are assigning on the last joint, as the link of the base is fixed, so it doesn't have any motion. So this is equal A1 times A2, and this is equal to this whole matrix. So C1, C2 minus S1, S2, C1, C2 plus C2 times S1 is C1 times S2 plus C2 times S1, 0, 0, minus C1 times S2 minus C2 times S1, C1 times S2 minus S1 times S2, 0, 0, and 0, 0, 1, 0. Now I need more space right here. So C1 times C2 now I will let A2 in evidence, and C1 times C2 minus S1 times S2 plus A1 times C1, and again A2 in evidence, S1 times C2 plus C1 times S2 plus A1 times S1 and 0 and 1. Okay. And now something that the book uses is a simplification. So it uses trigonometric identity of sum of angles. So something that we need to recall is sum of angles. And let me write this right here. Let's recall this. So if you remember, for example, cosine of 2x's, we can write as the same as cosine of x plus x, and this is just algebra. And now let's switch the sides. So cosine of x plus x, just switching the sides, is equal cosine of 2x. And apply now this trigonometric identity of sum of angles. We have that cosine of A minus sine of B. So two angles or two arcs is equal cosine of A times cosine of B plus sine of A times sine of B. And if we are summing two angles that are equal in quality, so it's the same as cosine of x times cosine of x, because both of these angles or arcs, they are equal, and this is the same as cosine square of x, and right here is the same logic. Sine of x times sine of x is equal sine square of x, and we can write that cosine of 2x is equal cosine square of x minus sine square of x. And now let's see if we can identify this trigonometric identity right here on the elements of this matrix. So let me just bring this right here, this part, and I will even put them side by side to compare. This first element right here, So we can write that cosine of theta 1 plus theta 2 and this is equal C1 2, not C12, C1 2. And also recall the identity for summing up angles of arcs of the sine function using the sine function. So let me just be quickly right here. So we can write that sine of 2x's, now again just using the algebra, is the same as write sine of x plus x, and now switching the sides of this fraction. So the identity, it says that a minus b is equal sine of a times cosine of b minus sine of b times cosine of a, and having the angles or the arcs with the same quality. In terms of qualities, we can write that sine of x times sine of x, cosine of x minus sine of x times cosine of x, and this is equal now. If you can notice, these terms, they are equal, so actually right here this sine of it changed to a sine of plus, because this operation right here, so this is 2 sine of x times cosine of x. And again, let me bring this right here to do a comparison and try to find a correspondence on the matrix, so we can simplify this matrix. Right here, these elements, we can write as sine of theta 1 plus theta 2, which is equal to okay, in this way we can simplify this matrix. And I will finish this exercise on the next video, and we will start another exercise. So this is all for now. Hope you like, hope you enjoy, and thank you.